Alright, I'm going to go through the solutions to the multiplication law of probability. And we're going to start with number 1. This requires you to know a little bit about cards. And if you didn't, I gave you 4 bullets up here to give you some facts about playing with cards. So you're going to draw 1 card from a standard deck of cards and find the probabilities of obtaining the following. So first one, you're picking 1. What's the probability we get a king? There's 4 kings out of 52 cards. And you can reduce that to 1 out of 13. Using elementary probability here. Probability you pick a heart. Well, there are 13 hearts out of 52 cards. Reduce that. Probability of a black card. Well, half the deck is black. Probability of picking a jack given clubs. Okay, so now this is your conditional probability. So it's out of all the clubs. So how many clubs are there? 13 clubs. And then within those 13, how many are jacks? Only 1. E, probability of getting a red queen. Well, out of 52 cards, how many red queens are there? There are 2, the queen of diamonds and the queen of hearts. So reduce that, you get 1 out of 26. Probability of getting an even numbered spade. So out of your 52 cards, it's got to be an even numbered spade. So 2 of spades, 4, 6, 8, or 10 of spades. So there's only 5 even numbered spades. Probability of red or black. Well, all 52 cards are red or black out of all 52. So if you pick a card, you're going to get red or black. We're not talking about jokers here. Probability of a jack or a diamond. On this one, rather than think fundamental or elementary probability, I'm gonna think of the OR formula. So that would be the probability of getting a jack plus the probability of getting a diamond minus the probability of getting both, a jack and a diamond. So there are 4 jacks out of all 52 cards. There are 13 diamonds out of all 52 cards, minus how many jack of diamonds are there? Only 1 out of 52. And so, adding this up, we end up with 26 out of 52. Actually, I added wrong. Let me fix that. It should be 16 out of 52. And we can reduce that. Let's see, 8 out of 26. Keep cutting in half. 4 out of 13. 8 or a 10. Notice that those are mutually exclusive events. So I'm just going to count them up. I got 4 8s and 4 10s, so 8 out of 52. And which is going to be 2 out of 13. Face card given red. So how many red cards are there? Well, half the deck is red, either hearts or diamonds. And out of the red cards only, how many are face cards? So we got the jack, the queen, and the king are face cards of each suit. So that's 6 out of 26, which is 3 out of 13. King, probability of a king or a spade. So I'm going to treat this like H, so that's the probability of getting a king plus the probability of getting a spade minus the probability of getting both a king and a spade. So there are 4 kings out of 52 cards, plus there are 13 spades out of 52 cards minus how many king of spades are there? Only 1 out of 52. So this is actually the same exact work that we would do on H, and we end up with 16 out of 52, which reduces to 4 out of 13. And the last one, probability of getting a king and an ace. Well, those are mutually exclusive events, which means they cannot happen at the same time. If you pick one card, it can't be both an ace and a king, so the probability is going to be 0. Number 2, let A be the event of picking a jack, B be the event of picking a club. Are A and B mutually exclusive? Meaning, can they happen at the same time? Well, can you have a jack of clubs? Yes, you can. So, are they mutually exclusive? No. Why? Because we can have both at the same time. Alright, B, you randomly pick a card and toss a coin. A is the event that you pick a king for a deck of cards. B is that you get heads in the coin toss. Are A and B mutually exclusive? So let's take a look. What's the probability of A and B? And that's going to be the probability of A times the probability of B given A. So the probability of A is that you pick a king out of the court, so you got 4 out of 52. And the probability of B given A. So that means you picked a king. So now you're going to toss this coin, and what's the probability that you're going to get heads in that coin toss? And probability of heads is the probability of heads whether or not you got the king, so it's going to be 1 out of 2. And so it's important to note that the probability of B is going to equal the probability of B given A just by the fact that you're doing two different things. Like, one is you're picking a card, one you're picking you're flipping a coin, and what you get on one is not going to affect what you get on the other. And so automatically we get that they are independent. And back over here, notice that when we multiply 4 out of 52 by 1/2, it's not going to be 0. It'll be something else, not 0. So they're not mutually exclusive. Alright, part C, you roll a number cube, which is a die. A is the event that you roll at most a 2. B is the event that you roll an odd number. Okay. So what's the probability of A and B? Okay, you're only rolling 1. At most 2. What does at most 2 mean? 2 or less. So A is the event that you get a 1 or a 2. B is that you roll an odd number, so that can be a 1, a 3, or a 5. So what's the probability you get in both cases? Well, that would be if you roll a 1. So that's the same thing. What's the probability of rolling a 1? So 1 out of 6. That's not equal to 0, so not mutually exclusive. Okay. So now let's say, hey, what's the probability of A happening? So rolling a 1 or a 2. Well, that's 2 out of 6, which is 1/3. And what's the probability of A given B? So that means you've rolled an odd number, so it's out of 3. Out of those 3 odd numbers, the 1, 3, 5, how many of those are how many of those are at most 2? Well, only one of them are, so 1 out of 3. So the probability of A is 1/3, and the probability of A given B is also 1/3. Therefore, A and B are independent. Alright, D, you roll a number Q once. The event that you get, so A is prime, so our prime numbers would be 2, 3, and 5. Remember, 1's not prime. B is the event that you get an even number, so 2, 4, and 6. Okay, so the probability of A and B, that you get a prime and an even. Well, there's only one even prime, that's a 2 out of 6. Notice that that's not 0, so A and B are not mutually exclusive. Okay, now the probability of A is 3 out of 6. There's 3 primes out of the 6, so 1/2. The probability of A given B, alright, so you've rolled an even number. There are 3 even numbers. How many of those are prime? Is 1 out of 3. And notice that these are not equivalent, so A and B are not independent. Okay. 16. What's the probability of obtaining 5 heads in a row when flipping a coin 5 times? So probability of 5 heads is going to be, well, probability of the first one's a head, 1/2, times the probability of the second one's a head, and third, and fourth, and fifth. That's one way to do it, and we end up with 1 out of 32. You can also use the fundamental counting principle and combinations and the fundamental counting principle like we did prior, but you can also use this formula here. 17. Suppose a satellite defense system is established in which 4 satellites acting independently have a 0.9 probability of detecting an incoming ballistic missile. What's the probability that at least one of the 4 satellites detects an incoming ballistic missile? So remember, when you see at least, think the backdoor approach, like we said before. So think about the opposite. Okay, so the probability of, in this case, at least one detecting is equal to 1 minus the opposite, the probability of none of them detecting, all of them failing, right? Which is 1 minus, well, there's 4 satellites. They have a 0.9 probability of detecting, so the probability of not detecting would be 0.1. So 0.1 times 0.1. So the first one fails, second one fails, third one fails, and the fourth one fails. So that's 1 minus 0.0001, which is pretty high probability of this happening. comes out to 0.999. Oh, one more 9, sorry. So we're pretty safe to say that it's going to be detected. 18. According to December 2007 Gallup poll, 24% of American adults have visited a casino in the past 12 months. What's the probability that all 4 randomly selected adults have visited a casino in the past 12 months? So probability, the first one is 0.24, and the second one 0.24, third, and the fourth. And you just multiply those together to get your answer, which is 0.0033, so not very likely. B, what's the probability that all 4 randomly selected adults have not visited the casino? So if 24% of them visited the casino, then 76% did not, so the 76% chance that the first did not, 76% chance that the second did not, and the third, and the fourth, and multiply that together, you get 0.3336. (19) left-handed people. In a sample of 1,000 people, 120 are left-handed. 2 unrelated people are selected at random without replacement. So find the probability that both people are left-handed. Alright, so the probability that the first pick is left-handed, so that's 120 out of 1,000. And we got one, right? And now there's 119 left out of 999, because we're not replacing anybody. And that comes to be about 0.0144. Find the probability that neither person is left-handed. Okay, so I want to pick a right-handed person, right? So if 120 are left-handed, then the rest of them, which is what, 880, are right-handed. So I pick a right-handed person, so one of the 880 out of 1,000, not putting them back. And I want the next one to be right-handed, so now there's 879 out of 999. And calculate this, it comes out to be about 0.7744. And C says find the probability that at least one of the 2 people is left-handed. At least one of them is left-handed. Well, again, I see that word at least, or that phrase at least, so I'm thinking backdoor approach. So that's 1 minus the probability that none are left-handed. And we just found the probability of left-handed in part B, so that's going to be 1 minus 0.7744, roughly, which is about 0.2256. Alright, birthdays. In a room there are 40 people. We'd like to find out the chance that at least 2 people in that room share the same birthday. Do you think it's likely? This is a very interesting problem. I wish we could do this in person, but not. Alright, but it is a very interesting problem. So first, find the probability that any 2 people in the room would have the same birthday. Right, so let's say my birthday is August 3rd. And so if I randomly pick another person, what's the probability that they have that same birthday as me? Well, there are 365 days in a year, so the chances are 1 out of 365. Second, find out how many pairs of people you can make out of 40. Alright, we've done this before. Well, it's like the handshake problem. So if I want to pair up 2 people, I have 40 options for the first pick, and then 39 options for the second pick, but order didn't matter, so I divide by 2 factorial, and go ahead and simplify that, and you end up with 780 different ways to pair up two people. Alright, so now we got some extra credit here. Try to find the probability that at least two people in a room will have the same birthday. Okay, notice the at least. Let's think the probability that at least two people have the same birthday out of the 40 is going to be 1 minus the probability that no one has the same birthday. Okay, so 1 minus something. Well, if there's 40 people, there are 780 comparisons. Okay, so for each of those comparisons, there's a 1 out of 365 chance that they won't have, so that they do have the same birthday. So there is a 364 out of 365 chance that they do have the same birthday, right? Alright, so the first pair, we got 365, 4 out of 365 chance that they don't have the same birthday. And then we look at the next pairing of two people. Pick another combination of two people. And again, there's a 364 chance out of 365 chance that they don't have the same birthday. And there are 780 pairs that we need to do this. And so there are going to be 364 over 365. There's going to be 780 of these products. So in my calculator, I'm going to type in 1 minus 364 out of 365, and I'm going to raise not the 1, but the 364 out of 365. I'm going to raise that part to 780 power. And whatever I get, I'm going to subtract that from 1, and that will give me the probability of at least two people having the same birthday. Alright, so I go ahead, turn to my calculator, crunch the numbers, and we end up with 0.8823. So with 40 people in the same room, there is an 88% chance, a little higher than an 88% chance, that two people in that room have the same exact birthday. Where most people would say, hey, it's very unlikely that that would happen, we just proved that it's actually very likely that that would happen. Alright, number 21. You got a multiple choice quiz, got 3 questions on it. Each has 5 answer choices. Only one of the choices is correct, and you have no idea about this material, and you're going to flat out guess. Alright, so what's the probability of answering the first question correctly? Well, there's 5 answer choices, so there's 1 out of 5, assuming that you only have to select 1, right? Let's find the probability of answering the first 2 questions correctly. Well, got 1 out of 5 probability for the first, 1 out of 5 probability for the second, so 1 out of 25. Find the probability of answering all 3, same kind of pattern here. And you get 1 out of 125. Probability of answering none of the questions correctly. Alright, so you got 4 out of 5 wrong answers for the first, 4 out of 5 wrong ones for the second, and 4 out of 5 wrong ones for the third. And so you're going to get 64 out of 125. And find the probability of at least, there it comes again, at least one of these questions correctly. So that's the probability So it's going to be 1 minus the probability that none are answered correctly, which is going to be 1 minus the 64 out of 125 that we just answered in part D. And we end up with 61 out of 125. Alright, number 22. Here, before I answer this problem, it's going to be easier to find out like the row and column totals. So I'm going to put those in here. Alright, what's the probability a person was a passenger given it was a female? So out of the females, which are 11,000, so probability it's a person given female, there were 4,000 passengers, and you can reduce that to 4 out of 11. Okay, B, find the probability that the person was female. So you picked one, so there are, so probability of female would be 11,000 out of 36,000, or 11 out of 36. Probability the person was a driver or male. Probability of driver or male, that's the probability of a driver plus the probability of male minus the probability of a driver and male. And so drivers, let's see, we have 27,000 drivers. Males, we have 25,000 males minus, how many are both drivers and males? We got 20,000, all out of the 36,000. And work through that, you get 32,000 out of 36,000. Reduce that to 8 out of 9. Okay, that was D. Oh, sorry, that was C. D now. Probability the person was a female passenger. So probability it's female and a passenger. So how many female passengers are there? 4,000 out of the 36,000. 1 out of 9. Alright, for E, probability the passenger was a driver. There are 27,000 drivers out of 36,000. Reduce that. Oh, I'm sorry, I read that wrong. I read it as a person was a driver. It says the passenger was the driver. Let's think through that one a little bit better here. The passenger can't be the driver, can it? They are mutually exclusive events, so 0. And last one, F, probability that the person was female given they were a passenger. So they're so female. Sorry here. This is F, probability female given passenger. So how many passengers are there? There are 9,000 passengers. Out of those 9,000, how many are female? We got 4,000, so 4 out of 9. Alright, I think we are on to our last problem here. So again, we have a table, and so let's find our totals here. Alright, A says, what's the probability that a randomly selected individual who died from cancer was a former cigar smoker? So what's the probability you have a former, okay, that's F there, former cigar smoker given they died from cancer. Okay, so out of those that died from cancer, there's 1,000. So out of those 1,000, 100 were former smokers. So you get 1 out of 10. Alright, B says, what's the probability that a randomly selected individual from the study who was a former cigar smoker died from cancer? So probably they died given they were a former cigar smoker. So out of the former cigar smokers, there's 7,100 of them. 100 of them died from cancer. So 1 out of 71. Alright, let A be the event never smoked cigars. Okay, I'll put an A there. B be the event current cigar smoker. Okay, are events A and B mutually exclusive? So probability of A and B is definitely going to be 0. You can't have them. If you pick one person, they can't be in both of those categories at the same time. So yes. Are events A and B independent? Well, the probability of A is 1,207,00 over 134,000, and the probability of A given B, well, B is out of 6,200 people, and how many of those belong to A? None. So that's 0, and so no, they are not independent because they don't equal each other. So no, since the probability of A is not equal to the probability of A given B. Alright, E, let C be former cigar smoker. Okay, I had it as F, I'm going to put C there now. And D, the event died from cancer. Okay, are events C and D mutually exclusive? Okay, so the probability of C and D happening would be 100 out of the 134,000, which is not equal to 0, so no, they are not mutually exclusive. Are C and D independent? Well, the probability of C is 7,100 out of 134,000, and the probability of C given D is going to be 100. So out of D, out of 1,000, which we already found is 1 out of 10. And we can already see that C is not going to be 1 out of 10, so they're not equal to each other. So no, since the probability of C is not equal to the probability of C given D. Alright, hope things are going well, and have a great day. B asks, are events A and B independent? And if they are independent, then we could say that the probability of A would equal the probability of A given B. And so I'm going to try them both out. So the probability of A is, A is the event of picking a jack. So picking a jack, there's 4 jacks out of 52, which is 1 out of 13. So if they're independent, it shouldn't matter. The probability of A should not change if B happened. So let's now consider the probability of A happening given that B already happened. So when we do this, well, B is the event of picking a club. So we picked a club, so now we're just considering all the clubs. And there are 13 clubs. And so out of those 13, how many, are A? So A is, how many are jacks? 1. So we see that the probability of A is equal to the probability of B given A, and because these two are equal to each other, we say that they're independent. So A and B are independent because the probability of A is equal to the probability of A given B. And so this is a check to see if you get independence or not. To check if it's mutually exclusive or not, remember mutually exclusive means that the probability of A and B equals 0. And what we found is that the probability of, going back to A, the probability of A and B is 1 out of 52. It's not 0. And so that's another reason why A is not mutually exclusive. C, let C be the event of picking a face card, and D the event of picking a king. Are C and D mutually exclusive? Well, let's look at the probability of C and D. Because if they are mutually exclusive, this probability will equal 0. So the probability of picking a face card and picking a king. Okay, so it's out of 52. And there are, how many face cards? Well, you got your Jack, Queen, King for each of the 4 suits. So we got 12 face cards. And notice that in counting those face cards, your kings are included in those 12. So we don't want to double count. So we're not going to, there's 4 kings, but those 4 kings are part of the 12 that we already counted. So it's just 12 out of 52. Either way, this is not equal to 0. And so because the probability of C and D is not 0, that means they're not mutually exclusive. Are C and D independent? Well, let's look at the probability of C. And the probability of C, so C is the event of picking a face card. There's 12 face cards out of 52. We can reduce that to 3 out of 13. And now let's look at the probability of C given that event D already happened. So if event D already happened, that means you picked a king. Alright, so there are 4 possible kings out there. The king of spades, clubs, hearts, and I'm missing one. Either way, we got 4 kings. Out of those 4 kings, how many of those 4 kings are face cards? All of them. So 4 out of 4, which is 1. So notice that the probability of C is not equal to the probability of C given D. And since that's true, we can say that the events are not independent. So since those probabilities are not equal, C and D are not independent. Alright, number 3 I did on the lesson video. Number 4, extra credit. Jane and Juan have invented a card game from a standard deck of cards. A hand of 3 cards is dealt. It's a winning hand if exactly 2 of the 3 cards are the same suit. How many winning hands are there? Alright, so let's first take a look at, let's say the first 2 cards that they pick up are the same suit. And the last card is a different suit. I'll put N for not the same. So the first card you pick, it really doesn't matter what you pick. And there's 52 options out there, right? So you pick any of the 52. But once you pick a card, now you've picked what that particular suit is. Let's say I picked a heart. It doesn't have to be a heart, but I'm just picking one of them. Say I picked a heart. So one of them in my hand is a heart, and if I want my next card to match the same suit as my first card I pick, well then I'm going to have to pick a heart. Normally there's 13 hearts, but I've already picked one, so there's 12 hearts left to pick. So I got 12 options. Now the last card I pick, I don't want to be a heart, right? It could be anything else other than a heart. So how many options do I have? Well, there's 13 in each suit, and there's 3 other suits, so that's 39 options. Okay, and so if I multiply those numbers together, that will give me the number of possibilities that I can get to the same suits first. But I could get the same suit first and last, and the middle one I get is not the same. Or maybe the first one I pick is not the same, and the last 2 are the same. So I need to add those options up as well. And if I work those out, I get the same 3 numbers as a product for the same reasons. And go ahead and work through that. And when you enter that into your calculator, you're going to get 73,008. Alright, number 5. If you draw 2 cards randomly from a standard deck, what's the probability that you get 2 of a kind? So 2 kings or 2 sevens, so on. So it's the probability of whatever you pick first, a 2 of a kind. And so it really doesn't matter what the first pick is. So you have 52 cards to pick from. Out of 52 cards, it doesn't matter what that first pick is. But then the second card, let's say again, we want 2 of a kind. Let's say my first card was a king, by chance. So I want my second card to be a king. Well, how many kings are left? Well, I picked 1, there are 4, so there's 3 left. Out of how many cards? Because I've already picked 1. There were 52, I picked 1. Now there's only 51 cards left. Well, notice my first fraction just reduces to 1, so it's going to be 1 times 3 out of 51. So 3 out of 51 is the answer to this problem. And let's go ahead and look at the next problem. We did 6 together on the last this set of notes, so we're on 7. George randomly draws a card from a standard deck of 52 cards, and Summer also randomly draws a card. George did not replace his card. What's the best approximation to the probability that Summer's card is the same suit as George's? It's the same suit. Alright, so George picked a suit. Let's say his suit is hearts. Okay. Part D, what is the probability the student helped set up and did not walk? Okay, so the probability they helped set up and did not walk, or, so plus, the probability they did not help and they walked. Okay, so that's the probability of helping times the probability of not walking given they helped, plus the probability of not helping times the probability of walking given that they did not help. So I just find those numbers. So probability of helping is 0.85. Probability of not walking given that they helped is 0.2, plus probability of not walking is 0.15, and probability of walking given that they did not help is 0.6. When you walk through that, you get 0.26. And for extra credit, alright, on E, to answer this extra credit, I'm going to refer you to another formula on top. This right here, the probability of B given A is the probability of A and B divided by the probability of A. It's a conditional probability, and we're going to need that. Alright, so here we go. We want the probability that a student, what is the probability that a student who did not walk, so we know they did not walk, helped set up. So that's the probability of H given that they did not set up. Sorry, they did not walk. So NW. Using that formula that I pointed out to you, that's the probability of H and NW divided by the probability of NW not walking. Alright, so the top formula, not too bad. We can find that one and I think we've maybe done that already. So that's the probability of helping times the probability of not walking given that you helped. I'm just going to work on the top part of this fraction real quick here. Probability of helping is 0.85. I'm gonna highlight that one right here. So it'd be going this direction right there. So that's going to be 0.85. The probability of helping times the probability of not walking given that you helped. So that'd be 0.2. Over. Alright, now working on the denominator. Now not walking. Well, there's two different ways to not walk. So that means either you helped and did not walk. That's one way. Or you did not help and you did not walk. So we're going to have to find both of those. And notice the first one we have. So the first one is this piece here, that direction, right? The second piece I'll highlight in green is going this direction. I'll highlight that one in green. So we've already figured out the yellow part, and I'll just put those numbers in. So we got the 0.85 times 0.2 but we can't cancel stuff out because it's plus something else down here. It's what I highlighted in green. So that would be the probability of not helping times the probability of not walking given that you did not help. Alright, keep going. 0.85 times 0.2 over 0.85 times 0.2 plus, alright, probability of not helping is 0.15, and probability of not walking given that you did not help is 0.4. And now it's calculator time. But make sure you multiply and add up everything in the denominator first before anything else. Okay? So let's see here. 85 times 2 is 170. And these would be 3 decimal places. And 0.15 times 4 is 6. Well, 15 times 4 is 60. But again, 3 decimal places. You could multiply top and bottom by 1,000. Actually, you just multiply top and bottom by 100, and you end up with 17 over 17 plus 6. Alright, 17 plus 6 is 23. So 17 out of 23 is what we end up with. Alright, number 12. A bag contains 10 balls, 3 red and 7 white. Let A be the event that the first selection is a white ball, and B be the event that the second selection is a white ball. Construct a tree diagram to represent the options indicating probabilities on the branches. Okay, so I'm going to draw my tree diagram like this. So I'm going to select my first ball, and it could be red or it could be white. And there's 10 balls, and at the first one, the probability that I get red would be 3 out of 10. The probability of getting white would be 7 out of 10. And then if I get red first, my second selection could be red or white. Well, if I've already selected a red, that means there's 2 reds left out of 9 balls left. If I selected a red first, then there's still 7 white out of 9 left. Now I'm going to extend the tree on the white side. So if my first pick was white, there are 3 reds left out of 9. If my first selection was a white, then there are 2 whites. I'm sorry, 6 whites left out of 9. Okay, so there's my tree diagram with probabilities on the branches. And that's all we were asked to do on part A. Part B, calculate the probability the second ball is white. Okay, so there are 2 ways that can happen. And I will, one route in yellow here, that's the route where the second ball is white. Or the other route would be the first ball's white and the second ball's white. So those are the 2 different routes where we can take, and both cases we get what we want. So probability of white is in this, so probably the second one is white, is the probability of the first one is red, so I'll do red 1, and the second one's white, or the probability that the first one's white and the second one's white. So then that's going to be the probability that the first one's red times the probability that the second one is white given that the first one is red, plus the probability that the first one's white times the probability that the second one is white given the first one's white. Just using my probability formula. So first one's red is 3 out of 10. Second one's white given first one's red is 7 out of 9. Plus first one's white is 7 out of 10. Probability is second one's white given the first one's white is 6 out of 9. So that's 3 times 7 is 21. 7 times 6 is 42. All over 90. Which is 63 out of 90. Divide top and bottom by 9. We get 7 out of 10. Which is what we would expect. What's the probability you get a white ball? There's 7 white balls out of 10. 7 out of 10. We just worked out all those formulas and still got it. Alright, are A and B mutually exclusive? Alright, remember to test mutually exclusive, you're going to look for this. What's the probability of A and B? Okay, and well, what does that mean? That means what's the probability A is the event the first one's white, and B is the event that the second one's white. So that's really saying, hey, what's the probability that I get the first one white and second one white? Using our formula, that would be the probability of the first one white times the second one white given the first is white. Alright, so that'd be 7 out of 10 times 6 out of 9, which is 42 out of 90. We can reduce that, but bottom line here is it's not equal to 0, right? And if it's not equal to 0, then it's not mutually exclusive. And so we're going to say no, because this is not equal to 0. Alright, are A and B independent? Well, we need to compare two things. Well, what's the probability of A? So the probability of A is the probability that the first one's white, so that's 7 out of 10. And now we gotta look at, well, what's the probability of A given B? And that's given the second one is white, what's the probability of first? That's a little hard because of the order of things, so here's what I'm going to do. We can, A and B are interchangeable, and it's going to be easier for us here to consider the other option. So like, what's the probability of B, which is the second ball white, because we did that already here and we found it was 7 out of 10. And now let's find out what's the probability of B given A. So B given A means you've already selected the first one white. Now what's the probability that the second one's white after the first one's white? Okay, sorry. So that would be 6 out of 9. And it's important to see that they're not equal. So are they independent? No, because the probability of B is not equal to the probability of B given A. 13. A box contains 4 bad and 6 good tubes. 2 are drawn out together. One of them is tested and found to be good. What's the probability that the other one is also good? Okay. So what's the probability that the second is good given the first one is good? Well, there's 10 tubes altogether, right? But one's already been picked. So now there's 9 tubes left. And there are 6 good tubes, but one of them has already been picked. So now there's only 5 left to pick from. So 5 out of 9. Alright, moving on to number 14. So we're asked to draw a tree diagram here, and if you read the problem, 2 things can happen. Either your house is robbed, or not robbed. And it tells us that the probability the house is robbed is 1%. There's a 1% chance. 99% chance it's not robbed. But then there's this cottage. And the cottage could be robbed. Or maybe not. And there's a 5% chance that the cottage is robbed and a 95% chance it's not. Okay. And we want to find, hey, what's the probability that they're both going to be robbed? So let's say, okay, probability a house is robbed, so that's event A. Cottage robbed will be B. Okay, so what's the probability of A and B? And that's the probability of A times the probability of B given A, which is 0.01 times 0.05. And that's going to be 0.0005. So a small chance that they're both going to be robbed. B says, what's the probability one or the other, but not both, will be robbed? And so I'm going to highlight those paths. So we can have the house robbed, but then the cottage not. Or we can have the house not, but the cottage is robbed. Okay? So, not robbed, I'm going to say NA, so not A. And cottage not robbed, B not B. Okay, so we have the probability of A and not B, or we have the probability of not A and B happening. And hope you're seeing the pattern. I'm going to skip a step and not write out the formula, but the probability of A is 0.01 times the probability of not being robbed, the cottage not being robbed, given that the house is robbed, is 0.95. Plus, not A would be 0.99. And then the cottage being robbed, given that the house is not robbed, that would be 0.95. Work through that, and we get 0.059. So about a 6% chance that one of them will be robbed. 15. Determine whether the events are independent or dependent. Alright. A says you roll 2 dice. A is the event the sum is even. B is the event that one of the dice shows a 3. Are A and B mutually exclusive? Are they independent? Explain. Okay. So I'm going to create a sum table. So we can talk about this. Alright, so A is the event that the sum is even. Okay, so the probability of A, let's take a look at that one. How many even sums are there? Well, you can count them up. So you got 1, 2, you got 3 4s, you got 5 6s, 5 8s, 3 10s, and 1 12. So 5, 6, 7, 8, 9, 18 out of 36. So half of the sums are even, half are odd. Okay. B is the event that one of the dice shows a 3. Just one of them. So what's the probability of A and B? So it's an even sum, and one of the dice shows a 3. So for example, like a 3 and a 1 make a 4, so that's even. Or should we go 3 and 3? It's a little subjective here. When it says one of them shows a 3, could we have both of them show a 3? It doesn't matter. I'm going to say, let's say no. So let's say we did a 3 and a 6. Oops, that doesn't work. A 3 and a 5 would work though. That would be 8. Let me erase the other one. So again, we're just going to say exactly 1 3, not both 3s. That's the way I'm going to answer it, but you could answer it with both and we'll come up with the same conclusion. You could have, okay, so we could also have this 3 and 1, or we have 3 and 5 here. So it looks like 4 out of 36. Notice that that's not equal to 0, so they are not mutually exclusive. Alright, now let's consider the probability of A given B. So one of the dice shows a 3, and so if only one of them shows a 3, I'm going to circle the ones that can happen. And so how many are circled? We got 5, looks like 10, so it's out of 10. And then how many are highlighted green? So out of those that are circled, how many are even? So we got 1, 2, 3, 4 out of 10. And that reduces to 2 out of 5. And notice that the probability of A is not equal to the probability of A given B. Therefore, they are not independent. So rely on these formulas to decide if it's mutually exclusive or independent.